Welcome everybody to today's webinar on chemistry search. My name is Marit Overbeke and I'm responsible for marketing within Ontoforce, and will moderate today's session together with my colleague Philippe Patin. And Philippe is our scientific leader within Ontoforce. So what's on the agenda for today? First, we are going to briefly introduce you to DISQOVER and the topic of today's session. After this, Philip will explain the chemical research data workflow and give a demonstration. After the demo, you have the option to ask a question using the chat function. Let me start by introducing you to our linked data platform, DISQOVER. The DISQOVER self-service knowledge discovery platform empowers you to link fragmented internal, public, and third-party data sources with semantic search technology to quickly reveal previously hidden insights. DISQOVER lets you explore and connect data from disparate sources to uncover new insights in a matter of minutes. And this will enable you to, first of all, master the flood of information, speed up your research and go to market of new treatment and products, and homogenize, link, and reveal hidden correlations. So let us take a closer look into DISQOVER for chemistry search, the topic of today's session. In early drug discovery, researchers need to access all available and also relevant information about compounds. This way, they can identify if similar compounds have already been tested, whatever toxicities and adverse effects, etc., has been reported. But what are the advantages of DISQOVER for chemistry research? First of all, you are able to search all relevant databases for compound properties, tests, and other relevant information sources. You're also able to combine chemical structure and property search capabilities through seamless integration with third-party chemistry plugins. You're able to make better decisions by identifying every possible piece of relevant information thanks to the power of semantic search. And also you are able to accelerate your research process and get a significant head over your competitors in the overall process of drug development. Philip will now start explaining the chemical research data workflow and give a demonstration, after which you will be able to ask a question via the chat function in the Zoom functionality. Philip, the floor is yours.
Thank you, Marit, for the introduction. So, hi everybody, good morning, good afternoon, wherever you are. My name is Philip Patin, and I will try to lead you through this webinar session of today, where we will explain how we work in a chemistry-related setting with chemistry-related data to integrate different data sources and to make meaning out of it. So first, looking at this slide to show you a little bit of an overview of how we process data, how we integrate data in DISQOVER. You see here centrally that DISQOVER takes a central place around different data sources, and in the context of a chemistry search or a chemical research, you have some specific data sources which are specific for the domain itself. So let's first start with DISQOVER. We have approximately 150 public data sources that we make available via DISQOVER. That's something that you already have here if you install the platform or if you use the platform. There is a possibility to add extra public data sources or third-party data sources. But then the most interesting thing is the internal data. The internal data consists of default data sources in different formats, could be spreadsheets up to databases, but also chemical libraries. Chemical libraries typically identified or containing structures, chemical structures, and this is something we can add here to our system. Via a cheminformatics pre-processing, we are able to make some meaning out of that and to semantically link that with the relevant data. The result is a knowledge graph which is constructed, which can be used in two ways. First, you can use the user interface as a human to consult and to search and to analyze the data, but you could also work with additional applications which can use this as an information resource to extract information, to use this information for additional visualizations or advanced analytics such as machine learning. If we think about an ecosystem or an architecture where DISQOVER could fit in, you see many different applications where we could connect to or which can work together. On the left side, you see again the data sources that we are able to work with, but we can also have additional processing steps which can extract more relevant information out of these data sources. Additional services could be the cheminformatics pre-processing that I just mentioned, or unstructured data annotations or other more advanced text mining or text extraction systems. That results in exchanging information with DISQOVER and having the possibility to also include different visualization services, and on top of that have the possibility to work with plugins. Plugins which could help here on this side, like I explained in the pre-processing, but also could be used in searching. You will see an example of that. As a downstream effect, you could also link out to downstream analytics platforms such as Spotfire, Seven Bridges platforms, or your own systems like Made in Jupyter or RShiny. We also are able to work with more complex structures or data structures like document repositories. And again, there is a possibility to link to applications which are consuming the data. Okay, that's the general introduction to what the platform is. What would I like to show today is giving you some examples of doing direct searching in DISQOVER, searching on a chemical name or a chemical structure. Indirect searching, meaning that we are first searching for something different and then link to related chemicals. And then also explain a little bit more detail semantic chemistry search. So that means that we will try to apply additional data and an additional data source, which is explaining chemical structure relationships. So how are different chemicals related to each other based on different levels of similarity. So this is the place where I leave the presentation and go to the demo. So this is DISQOVER, what you see, and I will first maybe start with briefly browsing around what you see here on this page. This is a test environment of DISQOVER, meaning that this is a demonstration environment of DISQOVER, where you see some specific information here on the top. I'm logged in already, so I'm able to see everything. But we have here a distinction between data and collections. If I click, for example, on data, I see here all the different data sources that we make available. Because this is a test system and this is a system which is connecting to our public data sources, I see here a distinction between public data and in-house data. The in-house data source is something I will explain immediately, but the interesting thing here is that we are able to select very specifically on the different data sources which are made available in how they are extracted. If I take a certain source like Kebi, you see that we have a number of data types defined, and one of them is chemicals, that we have a number of data types defined where information is put in. So we define different data types, the sources provide information for every data type, and all together we create one big overarching graph. This is the big graph. Interestingly here, we can also highlight what is the contribution of every source in the graph. So this is the flexibility you have to see how is the graph constructed, who is contributing to what. The result of this is a rather complex integration of different data sources into all these data types. And that could make people a little bit, make it difficult to search, but that's not the case because we have a system on top of that to allow you to search across all these sources. So this is like a default search screen. You see a text bar, and I just called it text search to make a distinction between the chemicals structure search. But you see here the different data types. The moment I'm starting to type a key term, we see the highlight of the results. So for the first thing I would like to show is searching on just a name. So I type the name of a chemical, and I find my hits. I can make Booleans, I can make constructions. This is all possible. These are default behaviors, but you see here some highlighting. Highlighting with a white background means just a text search, so just a hit. This term is somewhere mentioned in publications. But I see also a highlight with a green background, for example, here in chemicals. So the moment I click here, I go into chemicals and I see a dashboard specifically for the chemicals I would like to represent. This dashboard is dynamic. I can change the dashboard. I can customize the dashboard. I can see multiple pieces of information together, and I'm also able to filter. What you see here is, for example, data which is coming from via federation, where you see here the different types of mode of action. So some of these chemicals have an activity, a certain activity in bioactivity. These activities can be used to filter. What is also interesting is that I see a list of my different chemicals summed up here as a kind of a spreadsheet, and these are the hits I found. What I can do is I can inspect my molecule if I want. I can open a detailed page and see all the richness of the data that we bring together. So what we have here is a single molecule, but the single molecule is receiving information from multiple data sources. The multiple data sources are listed here with color codes, how they contribute to the data. So I was searching for raltitrexate, which is a term we are using here, and you see here the different data sources, which are all contributing with synonyms. But we can continue and see here descriptions, different types of descriptions depending on the source, all kinds of identifier representations. This is all relevant data which can be used to identify your molecule or to know more about this. We also provide link outs to the original data sources so that you can double check what is available about this data in different data sources and how have we aggregated this information. So it could be used as a quick search and lookup system for your chemical data, but it also means, and that's what we are showing here, that we can embed this data, your internal data, with all this public data. And then you can take the data, the subset of the data you're interested in as relevant for your specific case. So this is just text searching and landing on a chemical page. Second option is, instead of using text search, using the chemical structure search. And here we immediately apply two different plugins. The first plugin is Marvin.js from Chemaxon, which is a chemical drawing canvas. We are able to also deal with other drawing canvases, but for this example, we work here with Marvin.js. What happens is that when you draw here a specific structure or cut and paste a specific structure, we can send this to a third-party service which is doing a cheminformatics analysis, a kind of matching algorithm, which does or a substructure search, similarity search, or other types of searches. So let's just try this out and take a molecule that I'm interested in. So I have a molecular structure. I can just drag and drop this, and I would like to do a similarity search. I take the default thresholds and numbers, and I just hit the search button and I get 10 results. What happens here? The molecule is translated into a string-like representation. The visible molecule is like represented as a mol file if you're familiar with the domain. This is sent to the API of this third-party service, and the answer comes back. The third-party service could be different solutions. In this case here, you will see that this is the Chemantic service that I will explain for the search number 4. I have two types of hits. Some of my molecules that I'm looking for are small molecules and active substances. Some and most of them, or normally all of them, are chemicals. So I click on chemicals and I see here the information appearing again. So same thing, instead of searching on a search term and landing on my chemicals, I can do the same thing with structures. That also means that I can try to prune parts of my structure away, that I can look into that, that I can see how similar a molecule is to something hypothetically I'm drawing. So that's search number 2, meaning also, okay, this is a wealth of information which opens, and you also see here, that's an additional thing, the link outs to related data. So I was looking for a specific structure. I see my hits. I can take the molecule I'm interested in. I, for example, select my molecule. and I can link out to related publications. So what happens here is I'm starting my search with a chemical, I find a related information, and then I'm linking out to related publications which are annotated with this molecule. It allows me to search for the most recent literature, for example, take very recent articles in the last year, and I'm able to also filter on other parameters like the journal title or descriptors. For the sake of this demo, I can also show you that we can add easily other filter types. For example, I can show a bar chart, which is, and this data is, or this representation doesn't work, sorry for that. A bar chart, which is showing the different publication type. That should work here, which is showing the different publication types I can use. And if I want, I can use this as an additional criterion to filter. For example, show me review articles. So I started with a molecule, I found my molecule of interest, and I'm landing on a subset of publications. And if I click on that, I see my publications appearing. If you have access to the full text, we have the link outs to the full text. This also could be included as an additional source. Okay, so this is search number 2. Search number 3. Indirect search. So I'm looking for something different in first place, and I'm linking out to chemicals. Just an example, let's say that I'm interested in the term antimetabolites. Antimetabolites are a class of chemicals which are used in certain types of typically cancer treatments, but I'm interested not immediately in the chemicals, I'm first interested in the clinical studies. So I'm looking for clinical studies where the term antimetabolite is used. I find, and I'm looking here to a new type of representation here. I'm looking to a dashboard typical for clinical studies. What I'm able to do here is, for example, take a look to recruiting clinical studies and see what appears. For example, I see here specific subsets of clinical studies. Interestingly here also is that we combine different data sources together to combine this information, and you see link outs to different molecules. So what is possible here? I can say, okay, cool. I would like to go to, for example, the active substances which are registered or which are linked to these clinical studies, and I get an overview of active substances. For example, I pick here 5-fluorouracil as an example, and I see again a rich annotation of this molecule. This is a pharmacological molecule, so we have a lot of pharmacological related data, but if I want, I can link to chemical related data. What happens here is that if I follow this link, that I follow the link to the molecule itself and related molecules. You get a very extensive overview here of all types of related molecules to my basic structure. This is an indirect search. You can do even more hops if you want, depending on the relevance of your search or what you really need. You can always, if you want, land on chemicals or use this as an intermediary point to link further. For example, if you find something interesting, you can say, okay, this is maybe an interesting molecule. Can I link out to the patents? Again, here you have information which is loading here specifically for the patents. This is probably a timeout. Okay, use case number 4, I will go back to the presentation once more to explain what we have added here as an additional data source. I was explaining this indirect searching, which allows you to search on chemical structure relationships. But what does that mean? A little bit of explanation here. We have integrated a specific data source derived from semantics. So what is Chemantics doing? They are trying to apply the fair data principles, if you're familiar with the idea of making your data findable, accessible, interoperable, and reusable. In that way, your data is more robust and can be more easily integrated with other data sources. This is exactly what we also do with DISQOVER. The interesting part of this is that by applying these kinds of principles, that we can easily tap into the data of Chemantics. And how does Chemantics work? It means that it's a platform where you can load different data sources. This can be done in bulk or as a continuous load. They analyze the data. They look to standardize the structures and validate the structures. They further annotate the structures, and that's what I will show you how we have integrated this in DISQOVER. So they add metadata and make the data also findable for specific filtering criteria. They organize the data in a database, and then they make it available again for specific structure search, data exporting, or analysis. What is now the interesting part of this is that this is a system which can be run on top of the existing data sources, could be loaded. You could see this as a kind of additional data source. The nice thing of this is that they can tap into different data sources like we do. So on top of Drug Central, for example, Springer Nature, CABI, which is already available in DISQOVER, this data is processed by Chemantics and additionally annotated. So what is possible then is that this data can be made available for additional linking to knowledge aggregation systems, for example, specific databases which are capturing reactions, for example, which are specifically adding different layers of additional information. Document analytics, like DISQOVER is capable of doing feature extraction based on text. Here you can do feature extraction based on the structure or the names. Also, commercial compounds can be linked. For example, the registries or the catalogs of different chemical providers. But there are also possibilities like competitive intelligence, like patents, patent databases, or other types of databases. So if you start from that, the system tries to bring some structure into the mixture of information which is available sometimes in the different databases. So if you're familiar working with different chemical databases, there is a challenge to uniquely identify structures. You have different types of inputs. You see mol files, SMILE formats, etc., INCHI keys. And the interesting thing here is that sometimes certain chemicals are single structures, could be mixtures, or could be reactions. All of this can be handled, and what is done is a source database has specific IDs per source, and we treat it, or this is treated here as original materials. So the entries which are linked to a certain database are treated as original materials, and based on that, a number of normalizations are added to bring structure in the complexity. For example, here for this mixture, there is a normalization which is identifying different parts of a mixture so that you have different molecular graphs, are they called. And these molecular graphs are then further analyzed in other classes, which are always a reduction step in complexity. So what you get is, from a single source database, you get original materials which are identified in the source itself and also here in Chemantics. And then you have a split in different molecular graphs. Just to give an example what the value is of this, if you look in detail to these three molecular representations, these molecular representations are slightly different, but actually are the same molecule. And that's the challenge for the human eye or for a system. If you're not able to work with this or to recognize that these are similar, actually the same molecule, you maybe will split them up in three separate entries. So if you take a look to these three examples, Drug Central, HMDB, and CABI, they have different identifiers and the original sources, but they share the same ID, the same original material ID in Chemantics. They also share the same molecular graph ID. But now if you go one step further and we take a look to Kebi, there seems to be another entry where you have a small difference, a charge difference in the molecule. The original material is different because the representation of this molecule is slightly different. There isn't charge here. But they share this, again, the same molecular graph. So the normalization reveals that underlying the small difference in representation, there is the same chemical. If you now extend this a little bit and you create like a few hypothetical structures with other charge differences, you will get other original materials, but always the same molecular graph. And this is the power of how this data could be linked. Here you're able to distinguish if molecules are really different or if they share the same chemical building or the same chemical structure. So this is applied in the demo. And let's take a look to that. So we ingested that data from Chemantix to show you how it nicely fits together with the navigations and the searching you can do in DISQOVER. So let's just go back to raltitrexate, or we can also do another chemical structure search. And I will take another molecule and start my search. So what I've done is I just cut and pasted as a part of a molecule or a structure, and I get 8 results. And now we go a little bit deeper into what we see here as a representation. These are the results, and you see pharopenem as a first result, and then you can read from left to right the different levels of abstraction. So the molecule can be presented here, but if you want to, you can go to a molecular graph, a molecular framework, a ring structure, and this means that you can always reduce the level of complexity. If you take a look here to this ring with attachment points, which is quite unique here, you see that this pharopenem molecule that we recognized has a certain ring structure with a specific attachment point. What is now very cool is that we can link to the related molecules which are sharing the same attachment point, a ring with attachment points. So I started to do my search and I'm linking to all related molecules which share the same attachment points or ring with attachment points. So this allows me to go to a scaffold structure, another related structure, to see how are molecules related to each other. Just assume that you ingested molecules which are internal for you, specifically related to certain projects. I would like to see what is the relationship they have with molecules in a patent database or which are annotated in certain reaction databases. If we scroll a little bit deeper in the representation, we see here 2 other things appearing. You see here mesh classification, which is something that we have from the public space. Not all molecules are annotated, but you see here also a functional group annotation. And this allows me to even look to how is the molecule functionally annotated. For example, I can go to functional groups and take, for example, all the molecules which contain a primary amine. So just scrolling up, and this reduces my number of hits from 88 to 9 and shows me all the molecules which are having a primary amine. So you see the primary amine appearing here. So this also makes it possible, and this is an annotation which is also added by Chemantix, that you can use these structural classification to distinguish, to filter, to specifically look for specific subsets. There is even another possibility. Instead of choosing a functional group, you can even go for certain atom type bounds. So assume that you say, okay, I would like to see here a certain molecule which has a carbon-nitrogen bond. You can also select that and even select these levels of classification. So what is the interesting part here is that we can make a navigational journey, that you can select molecules, that you can use the structures, search again, navigate, and use the other levels also of abstraction. Just as a last example here for this navigation, we have a certain molecule here. I see here a normalized molecular framework. This normalized molecular framework is linked to 160 different chemicals. You see the split, the separation in different types, different abstraction levels, but you can go to all and then see how they are related to all, how all these molecules are related to this specific abstraction level. So this is a very nice example of combining text searching, integrating different data sources. That's what we currently have in DISQOVER, and also adding the power of semantic chemistry to interconnect or interlink chemical structures. This is the end of the demo. I think I can revert back to Marit. If there are questions, please come forward. You can ask your questions, and I see already some questions appearing in the Q&A.
Thank you, Philip. During your demonstration, a couple of questions already were put in the Q&A. The first one is of Raphael.
Yes.
Can the solution work also for plastic coatings or cosmetic ingredients?
Very good question. Absolutely. It depends on the data source. It depends on what you would like to ingest. We are showing here specifically chemicals which are related to life sciences, or more specifically to pharma, but it's actually in any niche of chemistry that we can work.
Okay, thank you.
Yeah.
And also a couple of questions by one or multiple anonymous attendees. Does the system support Helm?
Very good question. Not yet, but we definitely can make work out of that. We are looking together with the people from Chemantics to use this, but it's definitely something we would like to use. And maybe to explain to the rest of the audience, Helm could be used for larger molecules annotation, for example, like amino acids and amino acid variants, which could be then nicely annotated or also represented. And this is something we are exploring.
Okay, thank you, Philip. Another question that came in is, what kind of chem cartridge does it support?
What we can do here is we can tap into different data sources. So that depends a little bit on what is available for these typical systems that exist in a workflow. We have some experience already with integrating in different workflows. If there is a certain kind of export or linking linking to the data source, we can work with different chemical cartridges. Okay,
thank you. Another question that came in is, can it be deployed in AWS?
Absolutely. The system is available as an AMI, and we can completely set up what you see here as a deployment of Chemantics onto Force with DISQOVER, the Chemaxon plugins, and the different types of searching. All of this together can be deployed in AWS, but also in other major cloud vendor systems.
Okay, thank you. Another question that came in, Philip, is it possible to ingest chemical identified by smile strings?
Yes. So smile strings are not canonical representation or canonical IDs, but we are able to deal with that and use this as a representation and see how we can map this back to solid identifiers. That's also the reason why you have fixed identifiers in the different chemical databases that we ingested, but also what Chemantics is using as a data source as having an identifier which is also not resolvable. So you cannot reverse engineer the molecule ID, which you could do with an Inchi key or a smile string.
Okay.
Yeah.
And for now, I think the last question so far that came in is the following. What if I would like to connect to a data stream in a lab environment where constantly new molecules are added to a library?
Yeah, it's slightly related to a previous question. Yes, and that's a relatively new feature we have in DISQOVER. You see that we are here working with knowledge graphs and that different data sources are coming together. A typical implementation before was that this was rather static. We have the flexibility now to also dynamically ingest different data sources. So we are in this constellation, this whole setup is able to tap into rapidly changing data sources, so we can have frequent updates in a couple of minutes for newly added molecules.
Okay, thank you, Philip. I saw during your explanation another question came in.
Yes.
Can you connect this directly to an ELN?
Yes. When the ELN is, let's say, centrally managed as a database, yes, if we can tap into the database system itself, which is underlying the ELN. It depends a little bit on how to say this in a polite way, how modern the ELN is. The newer versions of ELNs have typically more connectivity, but it's not so difficult to tap into an ELN.
Okay, thank you. I don't see any more incoming questions so far. If you do, please feel free to put your question in the Q&A box or via the chat. But I think you answered most of the questions for today. If not, feel free to contact us offline and we will happily answer your additional question. But for today, I think we can wrap up this session. Philip, thank you very much for giving the wonderful presentation, and thank you all for joining today's session. And already enjoy the rest of your day. Thank you very much.